Okay, and share the screen. All right, let me put this away. All right, I was working on these slides during the exam, so they're a little maybe a little bit unfinished, but we'll see how it turns out. Okay, how was the exam? What was it? Really hard? Not hard enough? Too long?
Yeah, some problems
Anybody?
took some time.
Pardon me?
Yeah, some problems took some time to completely do.
Oh, okay. Um, okay. Some people thought it was pretty fair, I guess. All right. Yeah, I ended up giving you a little bit extra time because when I was looking at the exam at the beginning, Candace was telling me that the time limit was 2:30 and not 1:30. So I don't know what was wrong with Candace. So I'm glad you saw that it was 1:30. And um, to be safe, I did give you a little bit extra. Okay, so what I want to do is say a few words about operating system design. And, this is a kind of an unusual class because when I teach the compiler class, we end up writing a compiler. And when I teach object-oriented analysis and design, we do a project and demonstrate our good design. And when I teach database class, we build a database. But an operating system is just way too big to even attempt to build one. So all I can do is show you what an OS can do, and we do some simulations to try to better understand what the operating system is doing when it's managing processes or managing memory. Um, uh, After the spring break, when we come back, we'll start looking at things like, well, how does the operating system manage storage? How does it manage files, I/O devices? So there are other things that the operating system is doing for us, and we'll see what we can do to learn how basically it does all these wonderful things. Okay, but I wanted to say a few words about operating system design. In case you ever get onto a project at work where you're working on an operating system or maybe even designing a new one. Okay, so there are a number of goals, of course. Now you want to define all the right abstractions, and so now you have the command shell, you've got processes and threads, you've got inter-process communication, and you can see that I didn't get these slides quite right. Synchronizing all the threads and processes, managing memory, you got the file system you've got to manage. So there are all kinds of things an operating system has to do. And coming up with the right level of abstraction is important because you want the users of the OS to have one view of things. For example, if you're using an operating system, hopefully you're seeing files and not disk sectors. Okay, but if you go beyond or go below that level, when you're actually implementing all this, then yeah, you have to deal with disk sectors and keep track of, if you have a file, where does the file live? It could be scattered all over the disk, and you have to keep track of all of that. Okay? So a design goal is making sure you're at the right abstraction level and that you don't mix things up so that for some things the user is seeing a nice intuitive interface, and then for other things maybe you didn't get it quite right, and the poor user is looking at raw hardware or something like that. So you really got to be careful in getting the right abstractions and the abstraction layers. Okay. I think a lot of these slides will have bizarre animations. So let me check that before okay. Well, just ignore the weird animation if that occurs. Okay, so okay, let's see. Oh boy, let me get out of slideshow mode because um, something went wrong when I was putting these slides together. Okay, so we want to be able to provide operations for applications, and it could be a command language. You're going to have lots of system calls. Hopefully they'll all be POSIX compliant, but of course that is not an absolute necessity. But the industry is trying hard to standardize on these calls so that when you can port a program from one operating system to another, and if you are making POSIX calls, then hopefully you won't have to do a lot of rewriting of the application. Okay, user mode versus kernel mode. Okay, that basically allows the operating system to protect itself. You don't want the application programs to be going in there and messing with the process table, for instance. And then, so you want to keep the user programs running at a safe level. And if there are calls to the operating system, then you make a safe switch from user mode to kernel mode. And then you do the operation, and then you switch back into the user mode. Okay, that way user programs cannot inadvertently or even deliberately damage the operating system. Okay. Do you want to provide a GUI interface? I cannot imagine manipulating files, moving them around, renaming them, copying them, whatever, without having a nice GUI interface. I mean, it's all doable using command lines, but it's very hard to know what you're doing if you don't actually see those little icons on the screen. Little folder icons and little document icons and so forth. That is a very, very wonderful visual model to present to users. And operating systems now, that run on laptops and mobile devices and workstations have nice GUI interfaces. And so instead of making you type commands on the command line, you can manipulate icons on the screen. Now, I only gave you an introduction to the bash command line. Bash has a quite an extensive command language. And there are if statements and for loops and so forth. And so there are a lot of things you can do in the command line that you really cannot do with the GUI interface. For example, if you want to go through and rename all the files in your in a folder, let's say there are 100 files in there, and you want to rename them a certain way, maybe add a prefix to the names or something like that. Well, with the GUI interface, you're going to be doing that one at a time, and that could be very tedious. But on the command line, you could write a little bash script that will do that sort of thing. And and then that with IO redirection and with piping, the whole model of scripting in bash is that you write these little programs or well, they can even be bash scripts, and you can link them together using pipes and so instead of having to have to write one big monolithic program or script, you can write a bunch of little ones that each does a certain task and have the work pass from one program to the next using piping. Okay, and you got a chance to do some of that earlier in the semester. Okay, so command language is very important. GUI interface is very convenient and intuitive. And then, of course, for programs, you want to provide system calls, hopefully POSIX. Okay, and make sure you keep user mode and kernel mode separate. Okay. All right. So then, um, now, obviously, what an operating system has to do is keep track of multiple users, and you want to make sure that you isolate each user from all the other users. Certainly, you don't want one program or one user to reach into another user's space and do something. So you want to keep programs and users isolated, okay? And there are all kinds of protection mechanisms. The simplest one is making sure that a program stays within its memory allocation. So you start up a program, you allocate some memory for it, and you make sure that it doesn't try to address any memory outside of its allocation. Okay? Now, if all memory references are virtual and they go through a page table, then sure, you have more control because you get to specify what the entries in the page table are, and so that will be one way of preventing a program from trying to access memory that belongs to another program. Okay, you just don't have that kind of entry in the page table. Now, of course, one feature is to allow shared memory. Well, then the programs know what they're doing, hopefully, and so they can share memory, but in a very controlled way. Okay, uh, when bad things occur, you want to isolate those faults. You don't want one program that crashes to bring down the whole operating system. Of course, that does happen, but you want that to happen as infrequently as possible. Okay? So you put in all kinds of protections and catching exceptions and so forth to make sure that a misbehaving program isn't going to bring down the whole system. Okay? Managing the hardware, ultimately down below there's the hardware, and quite often the hardware has very ugly interfaces, and you could buy devices from different manufacturers, and they all have different interfaces. So one of the jobs of the operating system is to hide all that from the users and from user programs. They have low-level drivers that talk to the devices. So often those drivers are provided by the manufacturers of the devices, and they translate all the signals and whatnot into kind of a standard format so that the operating system can deal with all these various devices. Okay, and then up above, where there are the users and the user programs, well, you just send things to the printer, and magically things get printed, and you don't have to deal with all the control signals that the printer has. Okay, so you want to manage I/O devices. You have to manage memory. Okay, and we talked a lot about how memory is managed. There's paging, there's virtual memory, there's swapping. Um, all that is part of the operating system's job. And if you're going to design an operating system, you got to factor that in. Okay, dealing with interrupts. Okay, that's another big deal, because you have all these devices, and they're signaling saying that, hey, the data that you're trying to read is now available. So all these various signals and interrupts and so forth, operating system has to deal with those. Now, this is down at the hardware level, and the interrupts starts out as a signal on a line, and you have to um, uh, read that line or monitor that line, and when that signal comes, then you have to go through the various mechanisms to handle that signal. Okay. All right. Now, challenges that you have. If you have a successful operating system, and we all hope that you do, then it's going to be around for a long time. I mean, look how long Windows has been around. Unix has been around for 50 years. So if you have one that succeeds, you better expect it to live a long time, and be able to design it so that it can grow. When Bill Gates first put together DOS for the early PCs, um, it had a maximum of 640K, and people were saying that, oh my God, that is huge. Who could ever use 640K of memory? At the very early microcomputers, when they came out, you put in a 4K board, that was all of memory, and here we're talking 640K. So at that time, people thought it was a huge amount of memory. DOS had all kinds of hard-coded limits in there, and then all of a sudden, people realized that, hey, we need more memory. How are we going to do this? And I remember this. You would go out and buy a memory board that had maybe who knows how much more memory. I guess if you were rich at the time, you could buy a memory board that had all of a meg of memory on it. I mean, it was filled with chips, and you plug that into the motherboard, and then DOS had all kinds of tricks that it could play. Basically, you could buy software packages that did virtual memory, and so things are being paged in and out of the 640K of memory. So that was not realizing that this operating system was going to last a long time, and then needs would expand. For a while there, Windows could only get up to maybe 4 gigs, and then they expanded it. And of course, now a Windows can handle a lot more memory. Okay, so you have to make sure that you're not hard coding limits into the design. Now, OSs, of course, have become extremely large and complex. It seems like obviously Windows got bigger and bigger. Mac OS gets bigger and bigger. Linux keeps growing. Now, you can be smart about the growth. Instead of constantly adding new features into the operating system and making it bigger and bigger and slower, you can design it so that these new features are like plugins, so that you would incorporate that feature only if you needed it, and then even maybe give developers some control, that if you need this feature of the operating system, then you plug this module in there, and if you don't need it, you don't plug it in there, and that keeps the operating system as small and as non-complex as possible. Okay. Um, Similarly to what we were saying about making sure you don't put any hard limits, physical limits into the operating system, like a fixed memory size or whatever, you also don't want to put limits on what the OS can do. There is a strong need for generality. You don't want to limit an OS to just a particular set of applications, unless you are building a system only for certain applications. If you're trying to build an operating system that is going to be used for different kinds of applications, then you got to be real careful that you're also not limiting its capabilities. You just don't know how these systems are going to be used. I mean, it wasn't that long ago that people had never heard of streaming video and so forth, um, and now we do that all the time. So um, now another important factor is can this operating system work on different platforms? And so that's like saying that, hey, I want an operating system that can run on the Intel chip. I want it to run on the ARM. Think of Linux. Android operating system is basically Linux, and it's there are mobile devices that use the ARM chip. Um, well, most of them do, and of course Linux also runs on the Intel chip and the other chips, and so you don't want to put limitations into the OS that say it can only run on a certain chip. Okay. On the next slide here, I do talk about, I mentioned conditional compilation. Okay, I'll elaborate on conditional compilation in just a second here. Okay. Um, here's something that has really haunted a lot of OS developers, and I know this really hurt Microsoft for a long time, is to remain backwards compatible with some previous operating system. Microsoft had Windows, and the claim is that Microsoft was slow in adopting the internet and the cloud and so forth, because Windows was like an anchor on them, and they couldn't move past that quickly enough. They tried very, very hard to make sure that anything new that they did was backwards compatible and could still run on the older versions of Windows. And okay, that's very admirable. Customers like that, so that when they get new releases of the OS, it doesn't break all their applications, but then it also prevents you from doing some of the innovations that you might need and kind of break out of the box that you put yourself in. Okay. Concurrency is a really big issue. I know I spent a lot of time getting everybody uh, giving everybody experience with concurrency. That has to do with inter-process communication, synchronization, making sure that with mutexes that you don't have processes or threads stepping on each other, so the critical regions, all that kind of stuff. That is what concurrency is all about. And one of my soapboxes is that, boy, we all better learn how to write concurrent programs and multi-threaded programs, because hardware is multi-core, and you want to be able to take advantage of those cores. Okay. Hostile users. I'm constantly reading about hackers and ransomware, and I've worked for a number of years at NASA, and I tell you, NASA is a prime target for hackers. Either they're spies trying to steal secrets, or they're just people thinking that they want to brag that they broke into NASA. And so here's an interesting story. When I was working on two of the Mars rovers down at JPL, Jet Propulsion Laboratory in Pasadena, there was a firewall, to help protect the mission control computers. Outside the firewall, they didn't care what machine, what platform you were on. Inside the firewall, um, Windows operating system was not allowed, because they have found some security holes, and they were afraid that if people were using Windows inside the firewall, that hostile forces would be able to get into mission control. Now, I have to say that this was in the 2004, around that time. So I'm talking about, not very recently. I don't know if they're, well, let me tell you, they're currently, when I meet with NASA folks, it's not using Zoom. We use well, Microsoft Teams. And why not Zoom? Because when the pandemic first made everybody work from home, Zoom had some security issues, like having their servers in China. And so NASA said, hey, no way. So now we're using Microsoft Zoom, Microsoft Teams. And so I have to be able to use either one, depending on who I'm talking to. Okay. All right. So hostile users. But then, there's always sharing. So when you do have a group of users that do need to share, then you have to allow that too. And so if you look at the file system with Linux, and we'll be looking at it in a couple of weeks, you know that you can specify, basically who can open this file and look at it besides yourself. Now you can say, well, who can read it, who can write it. Obviously, you yourself can read and write files that you've created, but maybe you have a group of users, that you want to allow access, and you can do that. Or you can allow universal access. Anybody can read. Okay? So the three operations are read, write, and execute. Okay, and so if it's a text file, of course, you can allow people to read it. You can allow people to write to it. And if it's an executable file, you can decide who should be allowed to execute this program. Okay, so there you go. More design challenges for you. Okay. Now hiding the hardware. Okay. This is an example of conditional compilation. Okay. So you want your operating system to be usable on different platforms, and so you basically provide the source code of your OS, and then you have it compiled for each of the platforms that you expect this OS to run on. And so here you can see that we have to do some conditional compilations here using the preprocessor that the C and C++ compiler gives us. So you would have a configuration file, config.h or whatever, and you define, okay, I'm going to be compiling for the ARM chip, and the native word length is 64 bits, okay? And so you specify that in a config file, and then in all of your code, whenever it's important to know what operating system, what chip you're using, then you have this conditional compilation. So this says that, hey, if we specify that the CPU is the ARM chip, then you only compile this code, and then you do not compile the other code. And same thing with word length. If you're compiling on a machine with a 32-bit word length, then you would do this stuff. Otherwise, you would do the code here. And what's going on here in the right is we define register to be either an int or a long, so that later on we use register as a type. It's either going to be an register that can hold an int or a register that can hold a long. Okay, so these are the tricks you have to play in order to be able to have one body of source code that you can then compile for these different chip architectures and different word sizes and so on. Okay? So that's conditional compilation, and we have to make use of the compiler's preprocessor to do that. Okay. All right. Let's see, what else do I have here? Okay, so a few quotes from famous people. Simplicity. Okay. It, this is a interesting quote by Antoine de Saint-Exupéry. He wrote The Little Prince, the novel, but he had this interesting quote: perfection is reached not when there is no longer anything to add, but when there is no longer anything to take away. So a lot of people think that to make something perfect, you have to keep adding things to it. Okay, it'll be perfect if we just add this feature. But other people say that no, perfection is when things are as simple as possible. So you keep taking things away. And when you can no longer take anything away, then what you've got left is perfect. Okay. Well, speaking of simplicity, there's completeness. And Albert Einstein had a very interesting quote: everything should be as simple as possible, but no simpler, right? Yeah, sure. You know, to reach perfection, you take things away, but you don't want to take too many things away, because what you have left still has to be complete. Okay. And then efficiency. Okay, Tannenbaum is the author of one of the OS textbooks that I've been using to get material for this class. And basically says that if there's any feature or system call that cannot be implemented efficiently, then maybe you shouldn't have it. Okay, so okay. All right. And speaking of Tannenbaum, he does have this layered design in his book, and of course I stole the diagram out of it. And you can see, okay, that's very top. You have basically the API. Okay, so this is what the user programs call. API hopefully is made up of POSIX calls, and then we have the file system. Okay, so yes, programs do need to talk to the file system. Now, there'll be API here for reading and writing, opening and closing files and so forth. And of course, you're familiar with that. And then we have the virtual memory. Okay, and you want user programs to see the virtual memory and pretend that it's talking to the actual physical memory. And of course, we have page tables and so forth to create that illusion. Application programs should not be worried about where in memory the program is going to run. In fact, it could be broken up and put into different parts of physical memory. Okay, and we got the drivers. Okay, that talk to devices. Okay, here we have all the thread scheduling and mechanisms, interrupt handlers down here, memory management unit, and then whatever it takes to hide the actual hardware. Okay, so here we have a 7-layer operating system, and well, depending on your needs, you might need all 7 or maybe fewer. Okay. Now, performance, okay? As operating systems get bigger and more complicated, they get slower. I notice with the Macintosh that it seems like every new version of the Mac, it takes longer and longer and longer for it to wake up. If I close the laptop and later open it up again, it takes longer and longer for the thing to wake up. And I'm thinking, well, what is this thing doing? Operating systems have a lot of processes that they fire off at the beginning, and they're running in the background, to do various things. For example, there's a keyboard monitor. I mean, when you start typing, somebody has to notice that you're pressing down on those keys with your fingers, and it's a keyboard monitor that's running, that's keeping an eye on the keyboard. Same thing with the mouse. You move the mouse around. Well, somebody has to keep track of that, and so there's a process in the background that's monitoring the mouse. So when you turn on the computer, before you even start up your application, there could be dozens, if not more, of processes already running, and many of them are small, but they're out there, and the operating system has to keep track of them. All the inter-process communication mechanisms have to be in place to make sure that the operating system processes and your processes are going to work together. Okay, um, so anyway, that's why the OS is getting slower and slower, and that's why it's taking longer for it to wake up. It's because it's firing off, forking all these background processes. Okay, what should be optimized? Okay, should you put a lot of effort into optimizing everything? Well, the rule of thumb is that you run some profiling on your um, code. Now, profiling means that you have something, a monitor that's watching your program and finding out what parts of your code is going to be executed the most. And that's where you should concentrate your efforts in optimizing. And there's no point in optimizing code that's rarely used, right? In fact, optimization is quite an art. You want to make it either run faster, use up less memory, or use up less power. Okay, so you're making all these changes to the code to do all that, but you want to make sure you don't break the code or have the code behave differently. So optimization is something that takes a lot of work. Okay, space-time trade-offs. I'll show you a slide about this. Quite often, when you implement an algorithm, um, you can make it really fast, or you can make it really small. But is there a trade-off? If you make it really fast, are you making it bigger? And if you make it really small, are you making it slower? Okay, so you have to make sure you get that trade-off right. Caching, okay. We did touched on that subject. Things that are going to be accessed a lot, you want to keep in really fast memory. And certainly you don't want things that are accessed a lot to end up getting paged out onto disk. Okay, so caching is a way of buffering things that are going to be accessed very often, and you want to keep it in a place where you can access those things very efficiently. So it could be L1 or L2 cache memory. It could be main memory, but you certainly do not want it to end up on the swapping disk. Okay? Exploiting locality, we did look at that. It turns out that programs tend to cluster their accesses to memory. Once it starts accessing a certain region of memory, it tends to stay in that region. Okay, either so geographically that subsequent memory references are near, are close together in physical memory, or in time, that if you access a certain part of memory, it's very likely that very quickly you'll be accessing that area of memory again. So locality refers both to sort of geographic locality and also a temporal locality. Okay, and as I said, when you're optimizing, you want to do it for the common features. Okay? All right, let me show you this example that came out of the textbook. All right, so you need a routine that counts the number of bits in a byte. Okay, so all the 1 bits in a byte you want to count. Okay, and so all right, byte size is, let me see, maybe I can make this bigger. Okay, so byte size is 8, and you could write code that does it. Okay, so this gets compiled. You can see it's written as a function. Okay, you pass in the byte. It's got a loop that goes through and counts the number of bits in that byte. Okay, well, counts the number of 1 bits, I guess. Okay, and then it returns the count. Okay, so that's one way of doing it. Okay, well, the problem with this is that it's compiled code, so it does take up some memory, and is written as a function, and function calls have overhead. Yeah, yeah. In my compiler class, you learn that you know, things are pushed down onto the runtime stack, and then when you return, you got to pop off that stuff from the runtime stack. And inside this function, there's a loop. Okay, loops themselves have overhead. You got to initialize a control variable. You got to test it every time. You got to increment it. So the loop itself has overhead. Okay, so this way of counting bits in a byte is not terribly efficient. Okay, well, here's another one. Okay, instead of a function, let's make it a macro. Okay, and so okay, this is not a pretty ugly looking macro, but you can see all it's doing is taking the byte and constantly shifting it and ending a one to see if the rightmost bit is a one or a zero, and just keeps shifting until it has checked all the bits, all 8 of them. Now here, this is faster for 2 reasons. Number one, this will be expanded in place. So every time there's a call to a bit count passing B, instead of that being a function call, this ugly expression is going to be expanded in place. Okay, so there's no function call overhead, and there's no loop here, right? There's no loop here, and so the loop overhead is eliminated. Okay. All right. Well, here is yet another version. Okay. So we're going to count the bits in the byte. All right. So here we have a macro that looks up the bit count. Okay, and so we take the byte and we index into this table, and we don't even have the entire table here. We index into it and get back the result. Okay, so that would be very fast because it's just index into the table and get back the number of bits. We don't have to do all the shifting and so forth, and certainly we don't have the function call overhead and the looping overhead. Okay? So here we see examples of space and time trade-off, and this sort of thing happens all throughout the operating system. Little things that need to be done, and you can either write them as functions or as macros. But if you write it as a function and that function gets called a lot, then you have to deal with the function call overhead. Okay? And all loops have overhead. And so, is that a penalty that you want to deal with? All right, so okay, here we do it as a procedure. Here we do it as a macro, and this last one is also a macro, but the macro does a direct table lookup, and then of course you have to write this table. Okay, so this table has to be available so that when the macro expands into code that uses that table, it's there. Okay. All right. If you're really interested in operating systems design or designing any major software project, I highly, highly, highly recommend this book, The Mythical Man Month. Okay, and it was written by the, I guess he was the project manager for OS 360. Now, the IBM 360 was a major computer system from the mid to late 1960s, and writing the operating system for that computer system was a real challenge, because the 360 was designed to be both a commercial and a scientific computer. In other words, it can handle all kinds of commercial applications and then also scientific applications. And so that put a lot of demands on the operating system, a lot of challenges for designing it. And it was a major effort, and there were successes and failures. OS 360 is always used as a prime example of early mainframe operating system, and you'll read books about all the innovations that went into it. Okay, and then there are all sorts of books about what a disaster it was in terms of design and project management and so forth. I personally think that given the technologies that they had, given the software engineering experience that existed during the early 60s when this thing was all being done, I think they did a great job. And the 360, which then became the 370, that series of computers, believe it or not, it's still with us. IBM makes the Z series computers, which are backwards compatible, all the way back to the IBM 360. And why? Because there's a whole slew of programs that have been written. And I can tell you on the space shuttle, they are still running IBM 360 programs from the Apollo days. And why? Well, that's because those programs work, and nobody wants to go in there and rewrite them. Now, obviously, there's not an IBM 360 on the space shuttle, because you can emulate that huge mainframe on a chip nowadays, but they're still running that software. And so OS 360 was a major influence. I have some old operating systems textbooks from the late 60s and even through the 70s. In fact, my operating systems class that I took spent a lot of time looking at OS 360, and so these early textbooks that were on operating systems use OS 360 as the example operating system, and so whereas you pick up an OS book today and it uses Linux or Unix as the underlying example, and in this class I've tried to use Linux or Mac OS, which are both Unix-based as the underlying operating system example. The early books all used OS 360. So you read those books and you learn, here's how OS 360 managed processes. Here's how OS 360 managed files. Okay, and so you got a very mainframe point of view, but that, those are the days of the mainframe. Okay. But this is a very interesting book because written by I believe he was the project manager, Fred Brooks. And he laid it all out. This is what we learned. Building this really huge, complicated piece of software. And good lessons in there, okay? Talked about large project design. Okay, this is what he came up with. You spend a third of your time planning, 1/6 of the time coding, a quarter of the time testing. He calls it module testing. I guess nowadays the term is unit testing, and then system testing, 1/4 of the time. Okay, now does that add up to one? I guess I didn't look. Anyway, so you can see that you don't actually spend a whole lot of time coding relative to everything else. So designing and testing, that takes up a lot of your time. Okay, and here are some interesting revelations. People and time are not interchangeable. Okay, you cannot fully parallelize the work. You got to break things up into partitions, a large number of them, and then debugging is highly sequential. You cannot expect to be able to debug in parallel, and that you debug one thing, get it working, then you debug the next thing, get it working, and so forth. Okay. Adding manpower to a late software project makes it later. Okay, and I've been in this situation where, oh my gosh, we're falling behind. What are we going to do? What are we going to do? And the manager said, oh, hey, Charlie over there isn't doing anything. Let's throw Charlie into the project. Well, that gums up things so that things get even later. And why is that? Well, unless Charlie's a genius, Charlie comes in, has to spend time learning, and then somebody has to help train Charlie. And so the net result is that it makes the project even later. And so when your project is behind, there are other ways of mitigating the situation without throwing more people into it. But managers, they tend to say, well, if this project's behind, let's have more people jump in and work on it. And that usually makes the project even more behind. Okay? All right, so I highly recommend this book. It's actually a booklet. It's not a very large book, but it's fun to read, and there are a lot of revelations in there. And you can get it at Amazon. I don't think it's very expensive. Hang on, it's a paperback. Okay, there's the mythical main. Yeah, I mean it's not, you can probably find it in a library. It is such a popular book on how to the pitfalls of managing huge software projects, okay? or even being on one, let alone managing it. Okay. All right. Okay. Very quickly, where is OS design and development going? Well, of course, nowadays we deal with virtualization, the cloud, multi-core. Okay, I mentioned that. Large address space. Okay, that basically, well, in my Macintosh here, I've got. I think I've shown you this, but I'll show it again. I have 64 gigabytes of memory in this. 64 gigabytes. That is more memory than an entire company's computer center not that long ago. Okay, and so here it is sitting on my desk. So memory sizes are growing, and so operating systems have to be able to deal with these increased memory sizes. Often that means they have bigger page sizes because otherwise the page tables get really big. Okay, we got networking. Okay, that's not new, but certainly that's continues to be very important in terms of designing our systems. Parallel and distributed systems. Okay, that's related to networking. Multimedia. Okay, as I said, it wasn't all that long ago where people couldn't imagine streaming and storing movies and editing movies on the computer. Hey, we do that all the time now. Mobile devices, yeah. Who would have known that we'd be holding onto a computer in our hands that have more computing power than entire mainframes not that long ago. And sure, they need operating systems too. And then embedded systems. You're going to build a device that has some programmable chip in it, and hey, depending on what that chip is doing, you may need to embed an operating system in it. I'm sort of a Mac and iPhone, Apple type person, and so I'm not terribly familiar with Android. But my understanding is that the Android operating system is basically a Linux operating system, and so there we have operating systems in mobile devices. Okay. And I think that's all I have. All right. And any questions at all about this? Yeah, I thought it would be interesting to take a look at what are the trends and what are the challenges of designing an operating system. Um, I haven't seen in the literature um, what's coming. There's always the next new hot programming language. I haven't seen any articles about the next hot operating system that, after I graduated, which was a little while ago from college, there were a lot of articles about new operating systems, and because those were the days of you know DOS and Windows and well, Unix has been around since 1970, so it wasn't exactly new, but there were new distributions of Unix. We now have Ubuntu, and of course we have Linux and Debian and Red Hat. But I don't recall seeing recently any articles about, oh, there's this hot new operating system that's coming out, and so-and-so manufacturer is adopting it. Um, um, back a few years ago when there were new mobile devices, there were new operating systems that were being put on those new mobile devices. But then, the BlackBerry and some of those devices aren't around anymore. So, yeah. But I'm sure over the horizon, there's some new thing coming along. Either could be based on an existing OS, maybe a new distribution of Linux, or it could be something totally new. All right. Any questions? Okay. Yeah, sorry, I do tend to ramble, and I hope it was at least interesting ramble. I hope you all have a great spring break. Stay safe. Don't all rush over to Miami. I hear that that's a very popular place to go for spring break if you're on the East Coast, and they're having their issues over there. But I guess we'll get back together in a couple of weeks, and we'll start looking at how an operating system manages storage and file systems. Okay. All right. And we'll work on getting the midterm graded. Okay. Okay. Any questions? Okay. Then if not, I'm going to sign off then. Oh, there is a chat message, was there? Oh, okay, yes. Stay safe, everybody.